levels, we can look at the comparative analysis between the two techniques. In lesson 1, if you look at the notes, there are always two methods of analysis: gravimetry, what we not gravimetry, but sorry. Hello. So
Please,
I was
let's
saying that
mute our...
make sure you mute your microphone so that we don't interfere. So I was saying that in the lesson 1, you find that when you talk of methods of analysis, there are basically two types. There is what you call the chemical or the wet methods, and then there is what you call the instrumental methods. So I said before we discuss the volumetric, probably we look at comparative analysis between the two techniques. Now, but before that is that when you talk of a classical method or instrumental method, it all depends on the procedure that is applied. Because if, for example, you are given an example there where if you are determining HCl using sodium hydroxide in a volumetric analysis, where you check the completion of the reaction using a change in color as the endpoint. You use the color, the indicator to check the endpoint. Then such a procedure we say is classical. But it will turn to be instrumental if the endpoint is we are using a pH meter to determine the endpoint. So where we bring in an instrument to check the endpoint, then the process or the procedure or the method becomes instrumental. Because in instrumental, we actually use an instrument to carry out the determination or to carry out the analysis. So if you are doing volume titration and you are using a pH meter to check the endpoint, that process is no longer a classical method, but an instrumental method of analysis. Now, we are told that in classical methods, there is no mechanical or electrical instruments are used except simple apparatus. Then again, they actually use chemical reactions to quantify the analyte of interest in classical analysis. But in instrumental methods of analysis, they depend on instruments to perform or to carry out the entire analysis. So we are told that for that reason then is that classical analysis accounts for 10% of all the current analytical work, while instrumental accounts for over 90% of the current analytical work. Now, the classical methods are very sensitive, okay, less sensitive, sorry. The classical methods are less sensitive, while the instrumental are very sensitive. Similarly, for the classical methods, they determine one analyte at a time, while instrumental is a multi-analyzer. They can do up to 10 determinations at the same time. So they may determine several compounds at the same time. Now again, the classical methods work on a small concentration range of between 2 to 3 orders of magnitude, while instrumental work at more than 6 orders of magnitude. So they are, as he had mentioned before, they are quite sensitive, and their detection limits are up to the powers of 10, up to the powers of 6. They are very, very, very sensitive. Now, you find that again, classical methods, there's a lot of measurement, there's a lot of beakers and containers to be used. And for that reason, they are labor intensive. So they are labor intensive for the case of classical analysis. Here and there, preparing reagents and so on. But then for instrumental, they are quicker and cheaper. We normally talk of, in most of the instruments, you spike a very small amount is talk of spiking, a very small amount of the sample. You inject into the sample inlet, and then from there, the next thing you just get results. So it is a bit faster and also cheaper for a large number of samples. But for the case of classical, it is a bit labor intensive. Then a classical analysis, they are less efficient in data handling, for example, because in recording, okay, because in classical, we depend on recording our results, writing them down. So that can be very unreliable, because if you transfer that information wrongly, you get wrong results. If you lose whatever you are writing on your records, again you lose the data completely. While the instrumental, they are more efficient because majority of the equipments are automated, and therefore their results are very reliable. It can be stored for several years, and majority of the instruments are actually interfaced with computers. So they have an output. The output is a soft copy of the results. So soft copy can be stored. You can upload them into the internet. You can upload them into email, so they can remain for a longer time. So they are reliable, and it's not subject to manipulation. So there is no error when transferring the results during analysis. Now, then the advantages of, as much as we have some weaknesses, the advantages of classical is that they use very simple procedures. And majority of their procedures are often accurate. Okay. Now, in classical, we are dealing with volumetric analysis and gravimetry. Majority of them involve measurement, and measurements of volume and mass, they can be done with a lot of accuracy. So that is why generally the classical methods are very accurate. They are often accurate because we are talking of absolute measurements. They are based on absolute measurement of volume or mass. Now, the other advantage is that of course, method is based on absolute measurement, very straightforward measurements, very clear measurement of volume and weight. But when you talk of, when you move to instrumental, they measure absorbance, very complicated measurements that might not be so clear to us. Now, again, because they are simple procedures, they don't require any specialized training. Anyone can perform gravimetry, anyone can perform volumetric analysis, anyone can perform titration anyway. And again, the other very major advantage is that they are cheaper equipment. Majority of the instruments, the equipments that we use in gravimetry, in titometry, they are just beakers. We just need beakers, and beakers are not expensive to acquire. But on the other hand is that the advantages of instrumental are that one, they are automated equipment, making data or statistical handling very easy. So they are automated, and therefore you can be sure the storage of data is so good, it can be referred to in future in so many years down the line. Then they also use very small amount of solution. You spike very few mLs, very few microliters, and you have the results. But you can imagine in gravimetry, in volumetry, you are measuring a lot of volumes, and many others. So those are some of the few advantages of the two techniques. And then the disadvantages is that can begin with classical. Classical, one of the disadvantages is the storage of large volumes of solution is a challenge. Storage of large volumes of solution is a challenge. Here is a challenge in terms of the nature of containers you require, and then the space where you store. And again, instability of some reagents. Some of the reagents, once they are prepared, once to dissolve, you'll find that they are not stable because of exposure to the atmosphere. They tend to convert to something else, right? They convert to something else. So they are unstable, or the instability of some regions cause erroneous results. And then the fact that because you are using a lot of containers here and there, the need for clean glassware. You find that in instrumental, we rarely clean the instrument. The machines that we use, we rarely have a lot of work in cleaning those instruments. But unlike in classical, there is a lot of cleaning of the glassware. Now, on the other hand, then the disadvantages of instrumental. One of them is that they are basically expensive equipment. Even the instruments are a bit expensive. Then there are complex procedures that are being applied. Not everyone can run and majority of these big instruments. And because of that, they require some training. They require some skillful operator. So they require specialized training for you to operate those machines. Right, I think there's someone having a question. You can go ahead, Kikundi.
Yes, I'm asking whether we should assess these notes after the session is over.
Sorry?
Will you be able to assess these notes after the session is over, or we have these notes? You have sent them to us.
You already have the notes.
We have them.
The notes are in our portals.
Okay.
You already have the notes. I even shared in the. Yes.
I also wanted to request that you take us slowly. Hello.
Yes.
Because some of the notes are not legible now because we want to note some things as you talk. You can reduce the speed a little bit.
No problem.
Hello?
No, it's okay.
Okay.
So I was saying that the disadvantages of instrumental is that one is that they're generally expensive equipment. Majority of the labs don't afford to have them, except in very serious labs like Cambridge and so on, because of the cost implication. They are in millions. So unlike classical instruments, you find that they are relatively cheaper. Now again, you remember we said for instrumental, they actually utilize an instrument for or the property of the substance for analysis. So they actually utilize properties of the substance for analysis. And in most cases, they have follow very complex procedures, which require some training. So that is a disadvantage because not everyone will be able to do it, to operate. So it requires some training. And in fact, if you have been to these senior labs, the postgraduate labs in the universities, you find that each instrument have a specific person in charge so that he understands very well. So like the atomic absorption spectrometer in labs, it is being done by one person. You find that GCMS, that is gas chromatography mass spec, another person, a lab as an LCMS, the same. So unlike in classical where each one can do gravimetry, each one can do volumetric analysis. So I think that is the theoretical bit on the two techniques, the classicals and the instrumental. But the examples are given. Tachymetry and gravimetry are the examples for classical. For the case of instrumental, majority of them are HPLC and spectrophotometric methods of analysis, such as AAS. We have flame photometry. We have atomic emission spectroscopy. We have the GCMS, the LCMS, and many others, NMR, and so on. I think the examples in terms of instrumental and classical are captured in our very first topic. So if you refer the notes in the first topic on the methods of analysis, they have given an extensive list of instruments and then classified them either as instrumental or classical, instrumental or classical. Now, then we are told generally that so on the, of course, they are depending on the kind of analysis you are doing, you make a decision to choose which instrument to use. Okay, you make a decision on the choice of what instrument to choose, and there are a number of factors that you'll always consider. Of course, the most obvious is the availability of the instrument. If you are to choose an instrument, then you must know where it is available. Issues of cost again comes in. Issue of the accuracy and the precision of the results is also key, and many other factors that you need to consider. The time taken, the duration that will take for you to get the results. I think in most cases, we'll want our results to be as instant as possible, that once you are done in the lab, you have your results. So briefly, we can look at tachymetry analysis or volumetric analysis, which involves a measurement of volume. So we are told that this is a process whereby a titrant is reacted with an amount of analyte present in a sample. So the analyte is the unknown, while the titrant is a substance of known concentration that you actually use to determine the concentration of the analyte. Okay. So we in tachymetry is more or less about titration. It's more or less about titration. So the analyte is a test substance that reacts with the reagent solution of non-concentration. Now, this solution of non-concentration is referred to as a standard solution. And then they added from a burette mostly. So the solution of non-concentration is placed in a burette. And then, of course, the analyte normally in a beaker. Then you allow some amount of the analyte, the amount of the, sorry, not analyte, but of the burette to add into your analyte. Of course, having added the indicator for it to give you the endpoint, so that you are able to identify the endpoint. Now, so we are told that usually you use an indicator to determine the endpoint of the reaction, and then the titrant is the added solution. So the titrant is an added solution. Then you actually measure the amount of the titrant that you require to react completely with the analyte. Okay, so you measure the volume of the titrant required to completely react with the analyte. Once you measure based on the stoichiometry of the reaction, you can work back and be able to get the concentration of your analyte, of course, using some calculation on mole concept here and there. You'll be there. Now, I don't want to spend more time here, but there is a distinction. There is these terminologies that come in: the theoretical equivalence point, and then the end point. So when you talk of the equivalence point, you are talking of the point during a titration at which the amount of the titrant that is added is stoichiometrically equivalent to the substance being added. So we are talking of stoichiometry here. We are talking of the actual amount that is enough to react with the substance that is being determined. Such a point, we call it the equivalence point. And we have been explained how the equivalence point can be determined by plotting a change in pH against the volume of the titrant. So at the end point, there will be a drastic change in the pH, and therefore they'll normally give an S-shaped. So the inflation point gives the end point. So stoichiometry, when you talk about stoichiometric reaction, we are talking of that which is well defined, well balanced, and it is known between the analyte and the titrant. Like a reaction between an acid and a base. You know the formulas for the base, you know the formulae for the acid, you know the ratio, the mole ratio between the two reactants. So when you talk of equivalence point, we are talking of the actual amount of titrant that is added to the substance that you are determining, and that quantity or that point is what we refer to as the equivalence point. Then on the other hand, when you talk of the endpoint, the endpoint is a point at which the reaction is observed, so observed to be complete or to have reached a equivalence point. So this is what you observe, whether you are using a pH meter, whether you are using conductimetry, or whether you are using an indicator. That point at which you think or you observe that the reaction is complete. If it is indicator, the disappearance of the color, or whichever the case, it might be the appearance of the color. That point is what we do refer to as the end point. So end point does not necessarily mean equivalence point, but it is the point that you observe and say that the reaction is now complete, or I've reached some equivalence point. So equivalence point and and end point, they are related, but then they are very closely related, but they mean two different. They mean two different aspects at the same time. So here is about the actual endpoint that you observe, while equivalence point is the amount that is stoichiometrically equivalent to the substance that is being determined. Now, if it is using an indicator, it is that sharp change in the property of the color, either disappearance of the color or appearance of the color, depending on which indicator you are using. Depending on which indicator you are using. It can as well be a change in temperature, a sharp change in temperature. It can as well mean a sharp change in the refractive index, conductivity, or potential difference, or even the pH. If you are monitoring your titration using a pH, then you can be able to see or to observe a change in that property of pH. Right, so I think that is the two terms that I wanted to mention. Then the other one is standard solution, which I think we can spend a few minutes to look at. So a standard solution, as I mentioned before, is that we are talking of a solution of non-concentration. So a solution or a reagent of non-concentration. We normally use it to determine the concentration of the analyte in most cases. So you might be given a solution not knowing its concentration, you want to test. So you must have a standard solution. So this standard solution actually they are prepared by dissolving and you weigh some quantity of very pure substance and then you dissolve in enough water to make certain volume depending on how much you require, depending on how much. Now this material that we use to prepare standard solution is referred to as a primary standard. And you are saying it should be highly pure. So the purity here is very key to minimize errors when it comes to titration or any other determination. So we are told that it should be highly pure, around 99.9% pure. So it's referred to as a primary standard. And otherwise, if it is not very pure, it can give issues when it comes to the actual titration. Now, then the properties of this primary standard, apart from purity, is that they should be stable at room temperature and during analysis, during drying. It should be stable at room temperature and during drying. So apart from being very pure, so it should be as pure as possible, around even 100%. Although it is very rare to get a material that is 100% pure. Then the other property of a primary standard is that it has a high formula weight. And the formula weight here is to minimize weighing errors. So, when we talk of formula weight is that, when you are preparing very low concentrations, we normally get the number of moles times the formula weight. So if the formula weight is a bit small, then we end up measuring very small quantities of the primary standard. So if the primary standard is of high formula weight, then even if you are measuring very low quantities, very low concentrations, you will measure substantial amount. You will measure substantial amount of the primary standard. So that is what it means by, if you are using high formula weight, it will actually minimize errors when it comes to weighing that primary standard. Then number 4 is that they should be readily available. The availability of a primary standard is the physical availability in the market. The number 2, in terms of the cost, in terms of how much it should be affordable, okay? Because some things can be available in the market, but you cannot afford. So those 2 things, when you talk of readily available, is that they should be available physically in the market, and number 2, at a cost that we can be able to manage, right? And then finally, it should have properties required for titration, such as endpoint, stoichiometry, and rapidity. It should be able to react within a very short time to give the results. So those are the 5 properties of a primary standard, which we said a primary standard is the one that we normally use for preparing a standard solution. And a standard solution is the solution of known concentration that we actually use for purposes of determining the concentration of an analyte. So I hope so far so good.
Yes.
So the other important properties of this standard solution, we are told it should be able should be stable enough so that its concentration needs to be established only once. It should be very stable. Its reaction with analyte should be rapid so that time required between addition of reagent is reduced. That is, the reaction should be so rapid. As soon as it meets the analyte, it should react very fast so that as you add the other one, it reaches completion. Then we are told it should actually react completely and selectively with the analyte. So here is that it should react with your analyte to completion, and then selectively means specifically to a particular analyte. So it should be selective when it comes to reaction. If you are reacting HCl with sodium hydroxide, should react with the sodium hydroxide and nothing else. Okay, to minimize side reactions, which will actually consume your reagent. Then also, as I said, it should be stoichiometric. Stoichiometric, we said it should be defined, it should be well balanced, and the ratio between the reactant is actually very clear. Should be very clear. So I think you can look at the classifications of titrimetry methods. There are so many types of titrations or titrimetry methods. We have acid-base, we have those that are redox reactions, we have precipitation, we have complexometry titration, so and many others. So I think what I wanted to discuss is the preparation. Unfortunately, I don't have the notes on how to prepare, but I can try to explain. But you must have somewhere to write. Now, when it comes to this titration, we said one of the solution is standard. In other words, it should be of known concentration. And in most cases, you normally prepare those solutions. And how do we prepare is that we just use the usual, like I think here, you have the equation for the number of moles. So if the molarity is, for example, 0.1 molar, it will actually mean there are 0.1 moles in 1 liter of a particular solution. So for you to prepare 1 liter, for example, 0.1 mole of sodium hydroxide, you just need to get the formula weight of sodium hydroxide, then you multiply by 0.1 to get the number of grams that you need to measure. So you measure that weight and then you dilute to 1 liter. That will give you a 0.1 molar. Similarly to other solids like sodium carbonate, calcium hydroxide, if you are using them, that's how you go about it. Now, when it comes to acids, in most cases, they are obtained in solutions. Okay, we buy them from the market in solution form. We call them stocks. In maybe 2.5 liters. I think you can as well get in 5 liters and so on, and even 20 liters depending on the need. But in most cases, they are found in 2.5 liters. Now, when we buy them from the market, they are concentrated. They are highly concentrated. Okay, they are highly concentrated. Now, I want to take an example. We can begin with HCl and say, for example, we want to prepare 800 ml of 0.5 molar HCl solution, right? So maybe I can write in the chat and then give you the various steps that you need to follow. Now, the information that you require The information that you require for you to prepare this is that in those containers that are used to supply these acids, they contain what we call the specific gravity. Specific gravity is actually the density, okay, in gram per centimeter cube. So let me write here. So you can get a piece of paper, you can get some piece of where you can write how to prepare 800 ml of 0.5 molar HCl solution. So the information that you require is that you require the density of HCl. And normally they are either there is a 1.18 gram per centimeter cube. Okay, then the formula weight. Formula weight we can use that 6.457. Can use that. So you having those information. So if you have those information, the very first thing that we do, you want to prepare 800 ml.
Excuse.
Yes.
You have seen the density is 1.18, then volume?
Volume for? Formula weight. That 6.4. Eh? You are saying? Check. I've written in the chat.
You are giving us
check.
what we.
Yes.
In the chat.
I'm saying check in the chat. Check in the chat. I've written in the chat. Yes. Now, so the very first step that you do is that you'll want to work out the molarity of the stock solution, right? Molarity of the stock solution. So you use this, the density, which you are saying is the same as saying 1.8 grams actually present in 1 centimeter cube. That's what we mean by that density, that in every centimeter cube, there is a 1.18 grams of HCl. Then you calculate what about in 1,000, right? What about in 1,000? Now, so that will give you 1.18 times 1,000, you divide by 1. So it will give you 1180 grams in a liter. 1180 grams in a liter. But apart from that, you are also given the purity of HCl. It is normally given as 37%. Those are the information that are found. They are found in the container that we use to supply HCl. Now, so once you get 1180, I hope we are there. So I say the first thing is to obtain the molarity of stock solution. Now, so once you get 1180, we know that we are told that's only that 7% that is pure. So we consider purity. So we get that 7%. We get that 7% of 1180 grams per liter. Okay. So if you work out I hope someone is having a calculator somewhere. So you get that 37% of 1180.
436.6.
So you're getting 436.6. So that is gram in a liter, okay?
Yes.
Right? Now, then you can get now the molarity. Molarity in this case, you just get, yes, the number of moles in a liter, because you are talking of, these are 46.6 grams in a liter. You divide by the formula weight. So you have 436.6 gram per liter. You divide by 36.457 gram per mole. So this one you get in terms of moles in a liter, okay? Moles in a liter. So you divide that by 36.457. Then if you work out correctly, you are getting 11 point what?
97.
You're getting 11.97. Okay, approximately. Let's remain at 11.97. So that is the concentration or the molarity of the stock solution. So molarity of the stock solution, when you see that beaker having HCl, the concentration of HCl is actually 11.97 mole, almost 12. So molarity of the stock solution is actually equal to 11.97 molar. Now, once you have this, we use the dilution formula. The dilution formula is that now, you remember you want to dilute to how many? You want to get 800 ml, and you want to dilute from 11.97 to 0.57. So the dilution formula is the one that we have been talking about. You remember C1
V1
C1
equals
is
to
equal
C2
to
V2.
Yes, exactly. That is what I referring to. C2 V2. So what are our we take our C1 or the molarity of the stock to be the C1. Okay, so that is C1 is 11.97 molar. The V1 is how much we'll measure. That is the unknown. Then the C2 is 0.5 because you want to prepare 0.5 molar. And then V2 is the volume that you want to do what? To prepare, which is in this case 800 ml.
Cubic centimeter.
Okay. So I think from here it becomes straightforward. So we'll have 11.97 times V1 is equal to 0.5 times 800. So we'll have V1 to be equal to 0.5 times 800. You divide by 11.97. So we can 0.5 times 800. Then you divide by 11.97.
That's 3.41.
So I'm getting 33.417. So approximately that's 7.442.
33.42.
Yes, 3.42 approximately. 3.42. So that's how you can prepare. So you say to prepare 0.5 ml, 800 ml of 0.5 molar HCl, you measure. So this one you measure 33. Measure 33.42 centimeter cube of stock, and then you dissolve dilute in enough water, enough distilled water to make 1 liter. So that's how you can describe To make 800 ml, not 1 liter, but to make 800 ml.
So you add 800 ml of.
No, no, you don't. You measure 33.42, then you now add distilled water to make 800 ml. It is not that you take 33.42, then you bring 800. No, you make it to the mark.
To the mark, yeah.
Yes. So I think I've written there how you can describe the preparation. So I think that is you check the chart, and then again. So you find that the first thing is to be able to get the concentration of the stock. Once you get the concentration of the stock, you use the dilution formula, right? So depending on how much you want to prepare and what concentration. So different solutions will have different values for the density and for the purity. The nitric acid, the sulfuric acid, phosphoric acid, and so on. So we can have one more so that we get to understand. So I can give for sulfuric acid. So maybe you can say describe how to prepare. So you can have 500 ml.
ml.
I'm writing for you 500 ml of 0.4 molar sulfuric acid solution. Now I'll give the info. So for sulfuric acid, I think we begin with the density. Density for it is given as 1.84 gram per centimeter cube. Then we say the formula weight again. Formula weight we can use 98.01 is grams per mole, and then purity is 98%. So I think we have those information for sulfuric acid. Now, so can I give you a try? Can you try?
Yes, we can try.
Yes, please do. Let me give you a few minutes. You can. I think you will be able to. You'll be able to. So check the information on the chart. 1.84 gram per centimeter cube as a density. Formula weight can use 98.01. Then the purity is 98 for sulfuric acid.
Could we give answers? Hello. Hello.
Oh, sorry, I was saying once you are done, you give the final answer only. You give in the chat, then we can compare.
Okay.
I was handling some students. What are we doing actually? Hello?
The chat.
I was
There's a
handling some
question in the chat.
students.
I'm
There?
saying the chat.
Yes.
There's a question
The
in the
chat.
chat. Yes.
Okay.
Read up.
Okay.
There is a
Let me
question
do
there.
it. Yes. Let me try it.
Uh,
Class.
Yes.
So someone else, let's continue. Let's have a different answer.
I've
If you are
posted
getting the
mine.
same, I've seen. Let's wait for the other and see whether they are getting the same answer.
Okay.
Yeah, I see another one there. Just keep on posting them. Let's keep on doing it.
Malimo, these answers will be the same. Kindly repeat this thing for those who have not understand to understand.
We'll go through this second example together.
We have network. Like when you are explaining the other one, the network failed.
Okay, let's wait for the others to finish. We'll explain. Think we have more answers. Think we have more answers. So are we expecting more? We can work with those ones.
We can proceed.
We proceed.
Now let me. One volunteer can explain to us. I think because now we are getting the same answer, meaning that at least we are somewhere in terms of understanding. So if you feel like you can explain to us, you can raise up your hand and then I give you a chance. For the interest of those who maybe said maybe they were not able to understand in the first discussion. But from my observation is that quite a number of you are able to have understood actually. Right, I don't know whether it's Kikundi or Moniki. Moniki, you can
Yes.
you can take us through.
Okay, how to prepare 500 ml of 0.5 molar H2SO4. Given the density is 1.84, formula weight 98.01. Therefore, you first of all find the mass that is present in 1 liter. Therefore, you multiply the density by 1,000. That gives us 1840 grams per liter. Given the percentage purity, you find the percentage of the mass that was present, the percentage of the H2SO4. So you multiply the mass present in a liter by the percentage purity. So you multiply the 1840 by 98%. That gives us the percentage mass of the pure H2SO4 as 1803.2. Therefore, with the percentage mass, you divide it by the formula weight to get the molarity of the stock solution. So if you divide 1803 by 2.2 divided by 98.01, that gives us approximately 18.4. That is our C1. Therefore, we don't know our V1, so we use the formula of dilution C1 V1 equals to C2 V2. Therefore, our C1 is 18.4. Our V1 we don't know. Therefore, we say 0.4 multiplied by 500 is our C2 and V2 respectively. Therefore, you divide all through by 18.4 divided by 18.4. Therefore, our V1 will therefore be 10.87. Thank you.
Thank you, Monique. I think that is how you go about it. Those of us who perhaps they were not able to get the discussion earlier on, I think you are able now to have understood. So you first get the molarity of the stock, and you basically use the density. Density is more or less concentration, but then in 1 ml or in 1 centimeter cube. So what about in 1,000? So once you get the concentration, the mass in grams in 1 liter, you can get the concentration of the stock. Once you get the concentration of the stock, you talk of now diluting to the required amount and the required concentration.
Kindly repeat this using these figures.
Huh?
Repeat these this one using these figures as you
Which
did
figure?
in the HCL.
Huh?
I'm requesting you do this as you did in HCL.
In HCL.
As you did it, you quoted the figures, how you are cross multiplying and all that.
The one that I wrote in the chat.
Yes, I'm saying you repeat this one. Hello?
Yes.
The same way you did in the HCL, quoting these figures here, 1.83 grams density, such like.
So according to Monique, I think Monique was able to explain clearly, is that the first thing is that you have been given the density as 1.84 gram in cubic centimeter. So it actually implies that there is 1.84 grams in 1 cubic centimeter. Then now you will want to calculate what about in 1,000. So in 1,000, you will get 1840 grams per liter in 1 liter. But then from the information is that not all these are pure H2SO4. Not all of them are pure, but 98% are pure. So you work out 98% of 1840. You work out 98% of 1840. You are telling me, Maniki, you get 1803.2 gram in a liter.
Yes. Yes.
Now, once you get that is more or less concentration in grams per liter, you divide by the formula weight, which you have been given, 98.01 gram per mole, so that you get the molarity of the stock. So when you divide, you are getting 18.40 molar or moles per liter.
Yes.
So this is the concentration of the stock solution. Okay, as it is in the container, that is the concentration. So now for us to get the 500 ml and is it 500? Yes, 500, then 0.4. We take our C2 to be 0.4, or V2 to be 500. So we'll have on the right side 500 times 0.4 is equal to 18.4 times V1. You want to get the volume that you'll actually measure for you to prepare 500 ml of 0.4 molar. So we'll actually have 500 times 0.4, you divide by 18.4, which is saying, if you work out correctly, you get approximately 10.87, sorry, 10.87 cubic centimeter. And that is the volume that you will measure. You dilute or you dissolve in enough distilled water to make 500 ml. So that is how you go about it. And I think with these calculations, I believe that majority of us are able to understand. If you are not able to, you can always, you just need to expose yourself to a number of these preparation of this stock solution, or the molarity of the stock solution. Preparation of solutions in the lab. Those of us in high school, I think we normally give the technician to prepare, but that is how they go about it. But for them, they already know the stock solution, the molarity of the stock solution. So they just use the dilution formula. They just use the dilution formula to prepare the various concentrations they require.
Okay.
Right. So maybe I can give you one. You also try describe how to prepare. So this one describe how to prepare 600 ml of 0.5 molar nitric acid solution. So let me give you the molarity and the formula weight. So you can check the chart and then the density also. So the density is 1.13 gram per centimeter cube. Then what is the formula weight? You can use 63. You can use 63. Formula weight is then the purity. Finally, the purity is purity is 67%. You can use 67%. So I think the information that you require are given. So during your free time, you can just have a look at those.
Repeat the question, please.
Check in the chat.
Okay, thanks.
Give us the density kindly.
I've given it in the chat. Check the chat there. Right, so I think that one you can try during your free time. I want us to look at calculation of pH and pOH. So you can go back to the notes. Now, so the pH, as we've seen before, is that you calculate by getting the minus log of concentration of hydrogen. Then the pOH again is minus log of the hydroxide ion concentration, hydroxide ions, the concentration of hydroxide ions at the pOH. But then again, the pH and the pOH, they sum to 14. So pH plus pOH will give you 14. Then the Kw, which is the water dissociation constant, is 1.0 times 10 to the power minus 14. So it's always minus 14. Now, so I think there is for strong acids. For strong acids, it is known that strong acids will actually dissociate in solution completely. Same to strong bases, they luckily dissociate completely. For acids, it produces hydrogen ions. For bases, they produce hydroxide ions. But for weak acids, they dissociate to a small extent. Now, so the pH for strong acids is straightforward. Once you know the concentration of the hydroxide ions, hydrogen ions, sorry, you can be able to get the pH. So like the worked example that we have there, in the notes, we are told to calculate a pH of 2.0 times 10 to the power minus 3 molar solution of HCl. So here, this is a strong acid and it's a monobasic. That means it will dissociate to produce 1 mole. So then the mole ratio is 1:1, and therefore the concentration of hydrogen ions in this acid is also 2.0 times 10 to the power minus 3. So so to get the pH, you just get minus log of that value, and if you do it correctly, I think it should give you 2.699. So minus log of 0.002. Yes, it should give you 2.669. 2.669 as the molarity of as the pH of this HCl solution. I don't expect an answer now for that question. I just for practice. It was just for practice. Now, what I wanted to do is that although it's given the answer, these you are told to calculate the pH and the pOH of 5.0 times 10 to the power minus 2 solution of sodium hydroxide. So sodium hydroxide is a strong base, and it will dissociate to produce sodium ions and the hydroxide ions, and the mole ratio is 1:1. So the hydroxide ion concentration is similarly 5.0 times 10 to the power minus 2 moles in a liter. So you can, here you begin with the pOH. pOH will be minus log of 5.0 times 10 to the power minus 2. And if you do this, let me see. If you do it, you should be able to get that answer that is given up there. The pOH is 1.3. It is 1.3301. And then the pH, you said pH plus pOH should give you 14. So pH therefore will actually be 14 minus pOH. So it will give 14 minus 1.301. So that's what's giving you 12.7, approximately 12.7. So for strong acids and strong bases, you just need to get the dissociation equation, the equation that shows the dissociation of the acid or the base. And you know they dissociate completely when it comes to strong acids and strong bases. So from there you can get the concentrations of hydrogen. Once you get that, you can get the pH. If it is a base, once you get the concentrations of the OH, then you can get the pOH. Okay. Once you get the pOH, you can be able to work out the pH using the relationship pH plus pOH to give you 14. But now the challenge comes to when you are dealing with weak acids, which I want us to now discuss, getting the pH of a weak acid. Now for a weak acid, what happens is that weak acids, they partially dissociate. So whatever concentration you are given for a weak acid, not all of it will go into ionization. And therefore, this ionization constant will actually be used to calculate the amount that is ionized. Then from there, you can get the pH. So you are given an example of, I think this is acetic acid. So you are supposed to get the pH and the pH of 1.0 times 10 to the power of minus 3 molar solution of acetic acid. The formula is given that the ionization constant Ka is actually 1.76 times 10 to the power of minus 5. So I said for this, you consider the ionization constant because not all the ions in the acetic acid will go into solution because they actually the dissociation is to a small extent. Now, so you have the equation, therefore, the Ka is given by the hydrogen ion concentration times acetate ion divided by the acetic acid. So that's the formula for getting the acid constant. And the value is given. Now, at equilibria, it is taken that the concentrations of the acetate ion and the hydrogen ion are the same. And then you let them to be X. So that's why we have X times X. Then you divide by the concentration of the acid, the acetic acid. Now, so in that case, then you have you'll have X squared. Then you divide by 1.0 times 10 to the power of minus 3. So once you do that, you get the value of X to be 1.32 times 10 to the power of minus 2. So that is the concentration of the hydrogen ion and also the acetic acid, acetate ions. So once you get that, you can get the pH. Then from the pH, you can get the pOH. So I think you get the fact that in weak acids, we don't do directly because not all the ions, not all the acid will go into solution to produce hydrogen ions, unlike for strong acids. So here we must utilize the Ka, which is actually the acid constant, which gives you the extent to which that acid will actually dissociate. If it goes to a small extent, then that value will be very large. And then an assumption is actually made that the conjugate base of the acid. That is for this case, the acetate ion. If you see methanoic acid, we talk of the methanoid ions are the same as the hydrogen ion concentration. So that in that formula, the numerator you'll have X times X divided by the concentration of the acid. So in that case, you can get the concentration of hydrogen. Then from that, you can work out the pH. Then from there, you can be able to work out the pOH. So I think there is one here. There is one there, which I think I can write in the chat here. Calculate the pH and the pOH of 2.0 times 10 to the power of minus 2 solution of benzoic acid. And the benzoic acid is that the Ka, let me get the Ka value. Sorry, you can try to mute yourself, please. So in that question, I want to give you the Ka of benzoic acid. It is 6.5, you can write, times 10 to the power of minus 5. 6.5 times 10 to the power of minus 5. That is the Ka value for benzoic acid. So 6.5 times 10 . So I think you can try that using the values that I've just given you, and see whether you are going to get the pH and the pOH of that value. So using that value, you can be able to probably get the concentration of the acid. Then from there you can get the pH, then the pOH. Then finally for today, we can look at the puffer solution. So I said when you talk of a puffer solution, we are talking of a solution that resists a change in pH upon addition of a small amount of acid or a base. So they tend to stabilize the pH, okay? And the application is that they find application where you don't require the solution or the substance to change a pH when there is addition of acid or a base. We are told one of those substances is a blood. Our blood requires that it maintain at a particular pH. A slight change in pH can cause a lot of problems to humans. So PAFAs play a role. Now, a PAFA solution consists of a mixture of weak acid and its salt, or a weak base and its salt. So it can either be a weak acid and its salt, or a weak base with its salt. For example, so if you have a weak acid like NHA, then of the sodium salt of the conjugate base will actually be Na plus that A of the acid. So if it was something that contain chloride, then it will be sodium chloride on the other side, gives you a PAFA solution. So we can have, it can be, for example, acetic acid and sodium acetate. So that gives you a PAFA solution. But then we are told that PAFA capacity is the number of moles of a strong acid or a base, which is required to change the pH of 1 liter. 1 liter PAFA solution by 1 unit. So that amount, or that number of moles of a strong acid that is able to change the pH of 1 liter or a PAFA solution by 1 unit is called the PAFA capacity. So I think there's a derivation there for you consider dissociation of an acetic acid in that form. The equilibrium constant equation will be given by Ka, will be the hydrogen ion concentration times the hydrogen ion concentration times the acetate ion concentration divided by that of the acetic acid. Then you are solving the equation for concentration of hydrogen ions. You want to make hydrogen ion concentration the subject, we have that. And then taking logarithm on both sides, will actually, you break the right hand side so that because it's a multiplication, it's more or less of addition. More or less of addition. So we'll have, but then you are taking negative log. So we'll have minus log of the hydrogen ion is equal to minus log of Ka, then plus minus log of the acetic acid of acetate ion. But then we know that minus log of hydrogen ion is the pH, while minus log of Ka is the pKa, then minus that. So this formula is what we call Anderson-Hasselbalch equation, that pH is equal to pKa plus. So if you invert, it will be plus the log of acetate ion divided by acetic acid. So there is a typo in that final formula there. It should be a pH is equal to pKa plus log of acetate ion concentration divided by acetic acid concentration. And it is told that this equation will help us to calculate the pH of weak acid and its conjugate salt. So it indicates the pH. It actually indicates that the pH depends on the ratio of the acid and its conjugate base. Okay, and I hope there is an example. So there is an example that is given, and I think it is worked on, and you have the answer. So the pKa is a minus of Ka, minus log of Ka, and Ka is the acid constant for a particular acid, the acid constant for a particular acid. So I think you can go through that and then be able to appreciate the role that this pH plays, this PAFA solution plays. So we are told that for pH of human blood is constant at 7.35 to 4.745 because our blood contains a number of PAFAs. These are acid-base metabolites known as physiological PAFAs that protect against a pH change. Then proteins contain carboxylic and amino acid groups, which are weak acids and bases respectively. Hence, they are also physiological pavers. So they power the blood from changing the pH so much when they receive some amount of the acid and or a base. Right, so I think the next discussion will be on back titration, and we can work on this next week. If you can look at it next week, can look at the theory, then I can give you one or two example on how to, on the calculation, the quantitative aspect of back titration. Back titration is as titrations that are very common, and they are indirect in the sense that in the first reaction, the reaction is not complete, so that you need to get another reagent, okay, to react with the excess standard solution that was present. So they are actually two titrations in one. They are two in one. Of course, the first one might not be a titration per se. It could be a reaction between a certain reagent and a certain substance, which ensures that part of the standard solution remains, or it is in excess, and therefore it will remain. And if it remains, then you get another reagent that will react with that to completion. So in the calculation, you work back from the final, then going backwards to be able to get probably the concentration of the analyte. So unless there is a question, I intend to stop there for now. We can stop there for now, unless there is a concern.
We thank you for sparing your time to teach us in this lesson today.
Okay, welcome. We'll plan for the subsequent, because I think last week we did on Saturday and then Sunday and then Monday, is it? We'll see whether we can, but so far so good. Work on the cards so that by Sunday you submit. Then from there we can plan the next lectures. So bye for now, and see you next time.
When will we have our next class?
I'll discuss with probably between Wednesday and the weekend of next week, because I'm traveling on Friday. I'll be back on Tuesday, so I'll be available from Wednesday. So it can either be Wednesday, Thursday, or Friday next week.
Okay, thank you.
But I'll talk to. But Juma is always not in class. You are class rep. I don't. Are you present? This guy called Juma, the class rep. I've never seen him in class, so take note of that. That probably the class will either be from Wednesday or Thursday, not Thursday or Friday. Wednesday or Friday or Saturday. Next week, not this coming weekend, but the other one.
Okay, thank you.
Okay, bye for now.
At what time?
We'll talk.
Okay, hope every Monday so the cards in the card are behind it today in our portals.
Lecturer alikuwa amesema kuna class lini?
He said probably from next Wednesday.
Nasema hii class imeisha saa hii, alikuwa amecommunicate jana.
Yes, he communicated in during when we were attending the yesterday's lecture.
Sasa mungeweka
Sawa.
kwa group.
Mi hata nashangaa hii group iko na watu ambaye najua hata watu hapa hawakuji group discussions hawako nje. Ni sawa.
Why are you people lamenting?